Now we've covered sines and cosines and secants and tangents where they are raised to arbitrary powers, but every time we've dealt with them, it's been like sine to the fourth x, cosine to the fourth x, or secant squared 3 theta, tangent squared 3 theta. So the arguments, the actual angles that we're dealing with are going to be the same. But what happens when they're not the same? What happens when we have sine of 2x times cosine of 3x? How do we deal with that? Well, and the way to do that is actually deal with what's known as the product to sum formula. So I'm put recall with a question mark because depending on your trigonometry background, you may or may not have seen this, or at least not long enough to really let it sink in. But it's a really important, powerful concept that's used in a lot of applications, specifically things like, if you've heard the term like Fourier series or Fourier approximations, that this style and methodology can be used to manipulate those things. So it's important to kind of actually have this in your back pocket for when you need it. But anyway, it really comes down to two things. If you have sine of mx and sine of nx, what you can say, so if I have like sine 2x times sine 3x, I can rewrite that in terms of these. Now, if you know a little bit about your angle addition formulas, if you actually expand these angle addition formulas, they'll cancel out to get that. So they're really just the angle addition and angle subtraction formulas worked backwards. So you get this sort of 1/2 thing here. If you have sine and cosines mixed together, you have sine, sine. If you have cosines by themselves of different arguments, you get this. So, I could go through all that, but ultimately this is more of a reference thing. So, just sort of, not necessarily that you need to memorize it depending on what your background is, but it's helpful to at least be familiar with these concepts. Now, let's put them into play here. Well, one thing I was going to say, this hint here, choose m greater than or equal to n. So just because it's written, like this is written cosine 2x, cosine 4x, but there's no difference between cosine 4x times cosine 2x, right? That's, so multiplication is commutative. So when you're dealing with this sort of thing, don't just pick m and n. The reason why is because sometimes the negatives can mess you up. But if you pick m greater than or equal to n, so you just rewrite it in a convenient way, you'll never get messed up here. So, okay, I've got cosine and cosine. All right, so I've got these two. Let's check. Okay, so I'm going to get a cosine and a cosine here. So in this one, I subtract the smaller from the larger. So in this, it's 6 and 2. So that should have been a 4. Oh, no, it should have been a 2. My bad. So this should be 4, or this should be 2x. M is 4. I don't know what I'm thinking. I don't know. Maybe you never had it wrong. Anyway, this becomes cosine 2x. So when they're subtracted, it's 2x. When they're added, it's 6x. So then I can just split off the 1/2. I can separate it into two integrals. And then I can take the antiderivative to get 1/4 cosine 2x, or sine 2x, sorry, and then 1/12 sine of 6x, right? By the chain rule, you have that additional piece, plus c. So you're really just following a formula here. The next one, you have sines and cosines mixed together. So again, I'm picking the larger one to be my m. Actually, in this case, I can't. So this is really good. This is my mistake here. Right, I can't because the formula has me here. I actually can't do it like that, so that's going to mess me up. So now I have 1 and 3. So as a result, this is actually sine of negative 2x. So I have 1 minus 3. So this is sine of negative 2x. The reason why this is important because when you do sine of negative 2x, sine is an odd function. What that means is I can actually pull the negative out. I can pull that negative out to here. So I get negative 1/2. So since that was negative, this becomes positive. Over here, everything stays the same. So this is good practice for me. My apologies there. And again, follow the formula. Now this one, I like this one because this is an interesting one. Now that I have sines there, again, it wouldn't matter. But when m and n are equal, you get kind of interesting behavior. So if I look at sine, that's this top one here, I get cosine minus cosine. So when I take m minus n, so that's 5x minus 5x, well, it's cosine of 0. So I get cosine of 0 and then minus cosine of 10x. Now, cosine of 0, if you recall, is just 1. So I actually end up with 1 minus cosine of 10x dx, which antiderives to x minus 1/10 sine of 10x, again, plus your arbitrary constant. So you get some interesting behavior there when they're equal to each other, but it's not that big of a deal because in the case that they're equal to each other, you wouldn't usually write it like this. You would actually write it like sine squared 5x dx, right? So if you were doing it like that, it wouldn't. I'll tell you what, man, I'm messing this thing up all day, right? There's 1/2. So I apologize for that, but it's all fixed here. What you want to do in this particular case is instead of writing that, you would then use something like that half angle identity, which is 1 minus cosine double the argument over 2, which of course is exactly what we get here. We get 1/2 minus, we got the 1/2 1 minus cosine 10x. So it matches that angle reduction formula when they're equal to each other. But ultimately, it's really just following this. My part was I got a little too clever by half, wasn't really following the formula, was thinking I understood it. Sometimes you think you're smart, but you ain't, and you now have video proof that that is true for me.